Okay, so in this video, I'm going to talk about relativity and black holes, and then in the next one, I will finish up with the supernova type 1 and how we get heavier elements. So I'm going to start off with this idea of relativity, and before I can get super into it, I have to kind of go over the fact that when we measure speed, normally what we're measuring is speed relative to something else. So if I am standing by the side of the road and there's a car that drives past me and I measure his speed at 100 miles per hour, right here, and this car is going 100 miles per hour. That speed is compared to me standing still. If there's another car that is also going 100 miles per hour, and I ask this guy to measure this guy's speed, he looks out the window and he says, that car's not moving at all, right? If you and another car are going the same speed, you look out the window, it doesn't look like they're moving at all. So relative to this guy, this car is stationary. Relative to this person standing here by the side of the road, both of them are moving at 100 miles per hour. So normally what speed you measure something going at depends on how fast you are moving. And that works for almost everything. The one thing that it doesn't work for is light. No matter how fast you're moving, you will always measure light to be moving at the speed of light. It doesn't matter if you're moving at half the speed of light. You're still going to be measuring light to be moving at the speed of light. It doesn't matter if you're moving in the opposite direction from light. You're still going to measure it to be moving at the speed of light. So this works for everything else, but for light, no matter where you're measuring it from, no matter how fast you're going when you measure it, the speed of light is always the same. Okay? So, the speed of light is this kind of universal speed limit, right? Nothing can go faster than light. And when we think of speed, we normally think of speed through space, right? We measure it in miles per hour or something like that, meters per second, right? How fast we're moving through space. But in astronomy or in the universe or in physics, anything, it's not just space that matters. It's space and time, right? If I give you just a location of an event, you don't know what time it's at. If I give you just the time, like this is happening at this time, but I don't tell you where it's happening, I haven't given you all the information that you need. In order to describe an event, something happening in space-time, you have to give the location in space and the location in time, right? And so this combination of the two is called space-time. And we understand moving through space, but there's also this concept of speed through time, right? So if I'm just sitting here, standing still, I'm not moving through space, but I'm moving through time, right? Time is passing for me. I'm moving through time at the speed of 1 second per second, right? Every second on Earth, 1 second passes for me. So I have like a constant speed in time. And the way that we live our lives and in the regime of our daily life, that's fine. Our speed in time is constant and we can change our speed in space. We can go faster or slower in space. But when you get to the details of it, especially when you get to going super fast, it's not quite that simple. So our speed in time is not constant. what is constant is our speed in space-time. Everything moves through space-time at the same speed. And how that speed through space-time is broken up into speed in space and speed in time. So if you are moving faster through space, you have less speed in time because more of your total speed is going into speed in space. Right? So if I draw these boxes, these are all going to be the same size. So this whole box is my speed in space-time, right? All of these have the same speed in space-time. They're all the same size. But we're going to break these boxes up into speed in space and speed in time. So if I'm just standing still, then I have no speed in space. So all of my speed is speed in time. So standing still. If I start moving through space, some of this gets filled up with speed in space, right? So this is my speed in space. And then the rest is speed in time. And as you can see, if I start moving in space, I have less speed and time than I did when I wasn't moving at all. So I'm moving slower through time than I was when I wasn't moving at all. Now I start moving faster. And all of this is my space speed. Then I have even less speed and time. I'm going pretty slowly through time, right? If I'm light, so for light, all of light's space-time speed is taken up in speed in space. This whole thing, because this full limit is the speed of light. And light moves through space at the speed of light. So all of this is space speed. Which means there is no room left over for speed and time. So light doesn't move through time at all. For light, everything happens in the same moment. So for us here on Earth, light is created in the sun, and it takes 8 minutes for it to reach us, right? We're, standing still on Earth. It takes 8 minutes for light to reach us. For that light moving at 3 times 10 to the 10 centimeters per second, it gets created and it reaches Earth instantaneously. It happens in the same second. Light is not moving through time at all. Everything happens to it at the same time. So this is kind of confusing, but I want you to understand that the faster you move in space, the slower you move through time. So what does that mean? That means that the faster that you are moving, the less time passes for you. So if I'm standing on Earth still, and somebody gets in a spaceship, and they move this speed in space, and then they get where they're going. And I'm sitting there and I've got a stopwatch and I've measured how long it takes from them to leave till when they arrive. And I'm going to measure, say an hour. For them, on their spaceship, they've got their own stopwatch. And they started it when they left and they stopped it when they arrived. But their stopwatch says that only 45 minutes have passed. right? Because they're moving more slowly through time than we are. We're moving quicker through time, more time passed for us in the same difference in space-time than it did for them. This guy, if we measure him taking an hour from start to when he gets there, and he measures on his spaceship how long it took him from when he left to when he arrives, it only took him 15 minutes. And if you're moving at the speed of light, say something is 1 light hour away, it says we measured it taking an hour from it to go from us to that place. If it's moving at the speed of light, it'll say I left and I arrived at the same time. Because they're moving, this is not moving through time at all. This is moving through time shorter. So if you have, 2 astronauts and they're born on the same day, they're twins, and one of them stays on Earth, and one of them gets in a spaceship and goes really fast to another planet, and it takes them, 8 years to reach this other planet. So they get there and they're 8 years older. Maybe they've got a little bit of gray at their temples or something, and they call back to Earth and they say, hey, I want to talk to my brother. And their brother gets on the phone, and he's like an old man. He's like, it's been 40 years since you left. Because time passed more slowly on that spaceship, because it was moving faster than it did on Earth. Okay? So, that is one of the effects of something called special relativity. Right? Special, I remember it as special speed. It's the relativity that comes from speed. The faster that you go, the more that time slows down for you. You go more slowly through time. Right? If you are on your spaceship and you're counting the minutes, minutes are going by like this. And somebody on Earth, the minutes are going by like this. So it's been, 2 minutes for you, but it's been 15 minutes for someone on Earth. So one of the other effects is that you measure distances as shorter. So if there's like a ruler floating out in space, and you're just standing still and you measure that ruler, you're going to measure it as, 1 yard. But if you are going through very quickly, if you're whizzing by that going fast and you measure that ruler as you're going by, you're going to measure it to be less than that. So distant lengths are contracted. And then another thing that happens is mass increases. The faster that you go, the more mass you have. And this gets interesting because the more mass you have, the more energy it takes to make you go even faster. So as you build up your speed, you get more and more massive, and it takes more and more energy to get you to go even faster, to the point where you're getting so fast that to get you to go even faster would take an infinite amount of energy. And that's when you're getting up towards the speed of light. So nothing can ever travel at the speed of light. Nothing with mass, because you would need an infinite amount of energy to get it going that fast. Light can travel at the speed of light because it doesn't have mass. It's massless. So if you increase the nothing, you still have nothing. 200 times nothing is still nothing. So light doesn't have a mass to increase. So it can get up to going the speed of light. That's how fast it travels. But nothing with mass can travel as fast as the speed of light, because your mass increases the faster you're going. So that's kind of the idea behind special relativity. And I'm going to talk a little about general relativity as well. But one thing before I go deep into the idea of general relativity and what it is looking at these things, you get a very similar effect when not just when you're going very fast, but when you are going near something that has a lot of gravity. And the closer you get to something that has a lot of gravity, the slower time passes for you. So this is like in the movie Interstellar, why, Matthew McConaughey went to that black hole and he came back out and, only a little bit of time had passed for him. And he gets back and his daughter's an old lady. Because he went close to that black hole. Time slowed down for him. Right? He went more slowly through time than his daughter back on Earth. So she passed through time and got old. And he didn't because time had slowed down because he was near that black hole. So that is one effect of something called general relativity. And I remember that as general gravity. So, but the big idea behind general relativity is that mass creates warps in space-time. So if I think of space-time as like a big fabric that I've stretched out, and I'm holding it out. If I drop a ball onto this stretchy fabric, it's going to weigh part of it down, right? And it's going to create a dip. Now I have a tiny light little ball that's not going to create a dip. Then I'm going to roll along the side of this fabric, right? And if I roll it along the side of that fabric, it's going to go kind of in a straight line. But if I start rolling it closer and closer to this dip created by this big heavy ball that I put on my fabric, it's going to start curving and it's going to start falling in towards this ball. If I throw it faster, it's not going to curve as much. If I kind of just do it slowly, it's going to fall right into that ball. So gravity curves space-time. It creates this warp in space-time that curves space-time around it. And things still move in straight lines. They're just moving in a straight line through curved space, right? If I have like a pipe and I draw a straight line across it, and then I bend that whole pipe, that line is still a straight line through the pipe. It's just the pipe itself is curved. So now it's a curved line. But from the perspective of this curved pipe, it's a straight line, right? It's a straight line through curved space is a curve. So you get this, if I'm looking at it from the side, this dip looks like this. If I'm looking at it kind of from the top, about my object, and these lines and go into it like that. Right, this is looking down into this hole. So if I send something out here near this object, it's going to go straight. But if I send it right here, it's going to enter this straight line and curved space and start curving around. If it has a lot of speed, it's going to curve and go straight out like that. If it has just enough speed, it's going to curve and orbit, go in a straight line. If it has not very much speed, it's going to curve and fall in. Right? It's going to follow one of these curves. So how it reacts to this dip depends on how fast it's going at the start. Whether it just gets deflected whether it starts to orbit, whether it falls into it, right? And if this is a more massive thing, it's going to pull this dip down farther, and you're going to have to be going faster to just get deflected or just to orbit. It's going to take more speed to not fall into it. So things are still moving in straight lines again. They're just moving in straight lines through curved space, right? And this curved space is created by something with mass. It's not just matter. It's not just things that have mass that move through straight lines in these curved space. Light moves too. So when light gets near something that has a lot of mass, it's going to curve. Right? I showed, if something's going slow, it's going to fall in. If something's going medium fast, it's going to orbit. And if something is going really fast, it's just going to get deflected. So light is going really fast. So when it gets close to something that has a lot of gravity, it's going to get deflected and it's going to bend. And we see this happening with a phenomenon called gravitational lensing. So if you have something that has a lot of gravity and there's a star behind it, it's going to come off this star and bend around this, this way. So we're down here on the Earth, and we think, okay, light moves in a straight line. So we think what we see is a star here. And we see a star here. Right? And also, it can bend over it, so we'll see a star out here, and we'll see one on the other side of this board. But it's really right there. It's just the light has been bent around this big object. So, they tested this by taking a picture of the night sky, when there's nothing there. So these you can't see. These aren't there. You just see this, right? Take a picture, and this is the one you see. And there's no star here, no star here. And then during the day, during an eclipse, when the sun is right at that spot, then you take another picture, because the stars come out, and all of a sudden, this star has appeared here and here. Because they're not real stars, they're just images of this star that's been bent. Okay, so light also moves in this, it also curves as space-time curves. So it's still moving in a straight line, just through curved space. Okay, so that's this idea of gravitational lensing. This is how you can get like smears around or something. Okay, so looking at this homework problem, which of the following are predictions of special or general relativity? So the clock in a spaceship traveling at a high velocity with respect to Earth will run more slowly than the clock on Earth. And that's true, right? If you're moving faster through space, you're moving slower through time, so your clock's going to move more slowly. If you're in a spaceship moving at 0.9 the speed of light and shine a flashlight in the direction of travel, you will measure the speed of light beam to be 0.1 the speed of light. So that's not true. Remember, no matter how fast you're moving, the speed of light is always going to be measured at c, which is the speed of light, or 3 times 10 to the 8 meters per second. Time moves more slowly as you approach the event horizon of a black hole. That's true, right? Just either you get really close near something that's really big and or something that has a lot of gravity, or you go really fast. And then mass creates warps in the space-time fabric of the universe. That is true. That is the idea behind this general relativity. Okay, so now I can talk a little bit about black holes, since we've done that. So, we talked for the last quiz about neutron stars. And when you get a supernova type 2 explosion, this core collapse supernova, you're left with this neutron star core. And it is held up by something called neutron degeneracy pressure. And this is like the last type of pressure that can hold up. So you have gravity pulling in, trying to pull everything down and in deeper and deeper and deeper and compress it tighter and tighter and tighter. And you have neutron degeneracy pressure pushing back out and halting that collapse. And gravity increases with mass. So if you add more mass, you have more gravity. And neutron degeneracy pressure can only hold up against like up to maybe 3 or 4, like up to about 3 solar masses worth of gravity. So if you have, during this explosion, stuff can fall back onto the neutron star, like gas and other stuff, and the neutron star will gain mass. And if it gains more than about 3 solar masses worth of mass, then this gravity will go up, and the neutron degeneracy pressure can't push back against gravity anymore. And so the whole thing will collapse. And nothing will push back against this collapse. So gravity will bring everything in tighter and 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 tighter until all of this mass is compressed into a single point, right? It's so small that it's just essentially no size at all. You know, it's smaller than the head of a pin, like teeny, 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 tiny, to where it basically is no space at all. It's just a single point in space, and all of this mass has been compressed into that because there's nothing pushing back out against it anymore. So we call that a black hole. And one thing to note about this black hole is that its mass hasn't changed, right, from when it started. Its size has changed, right? You have your mass, and then it starts to collapse. So its size has changed, but its mass hasn't changed. So if you are outside of, like, that original size, gravity is not going to feel any different for you when this thing collapses into a black hole. So if you draw these dips in space-time, you know, this is something, and then this is the same black hole. Right, this part gets deeper. So we'll call this, you know, this is down here, this is the edge of your object. And the black hole is just a single tiny point. So this really goes down and down and down and down and down and down kind of forever. But if you're right here, your curve in space-time looks the same as if you had something that were the same mass but wasn't a black hole. So if the sun turns into a black hole, our orbit around the sun wouldn't change at all. Gravity wouldn't feel any different. We wouldn't have the sun putting out light in the sky, and so obviously that would be really different. But we wouldn't feel a different pull of gravity, right? Because if we're out here, gravity comes from this slope, this change in space-time, and it's the same no matter how deep this is. You know, it doesn't matter if this ends here or goes all the way down. It looks the same to us from right there. So nothing would change for us except for, you know, there wouldn't be any more light in the sky and we'd all die because of that. But gravity-wise, nothing would change if the sun turned into a black hole. So since for a black hole, there's no real size of the actual physical black hole, right? It's so tiny, it basically has no size at all. We can't really talk about its radius, but we can talk about something, an effective radius for it. And for the effective radius, we choose the radius at which light cannot escape from it. So outside of this effective radius, light is fast enough to get away from this black hole. Inside this effective radius, light is trapped inside this black hole. And to understand how that works, we have to talk about the concept of escape velocity. So if I, here on Earth, take a ball and I throw it up in the air pretty slowly, it's going to go up in the air and it's going to come back down. Right? Gravity's going to pull it back down. If I take a rocket and I strap a big engine on it and I send it up into space really fast, it's going to go up into space and it's not going to come back down. Right? So that tells me that somewhere between that two speeds is the limit for where I'm going to go up and not come back down anymore. Right? If I go below this speed, I'm going to go up and fall back down. If I go faster than this speed, I'm going to not come back down. And so that limit is called the escape velocity. Right? If you go faster than the escape velocity, you can escape the gravity of whatever you are trying to get away from. So the formula for escape velocity is the square root of 2gm over r. M is mass you are trying to get away from. R is your distance from the center. So if I want to know how fast something has to go to escape from the Earth, to not come back down, then I'm going to put in the mass of the Earth here and where I'm starting from. So if I'm starting from the surface of the Earth, then I'm going to put the radius of the Earth here, right? If I'm starting from higher up, then I'm going to put the radius plus how far from the surface I'm starting, right? So it's distance to the center of the Earth in this case. Or if I'm trying to escape from the sun, this would be like distance from the center of the sun, and this would be the mass of the sun. Okay? So for this critical radius of a black hole where light can't escape, that means that at this critical radius, which we're going to call the Schwarzschild radius, so when the radius is the Schwarzschild radius, the escape velocity is the speed of light. Right? At this radius, light can no longer escape from this black hole. Outside of it, light is going fast enough to not fall back in. Inside of it, light is not going fast enough and gets trapped inside the black hole and falls back down to it. Right? So at this limit, at my Schwarzschild radius, the escape velocity is the speed of light. So I'm going to take my formula for escape velocity and I'm going to substitute in these two things. Instead of escape velocity, I'm going to put C. And instead of R, I'm going to put my Schwarzschild radius. So 2gm over r Schwarzschild. Now, I want to know how big is my Schwarzschild radius. So I want to solve for this and get it on one side by itself. So to get rid of this square root, I'm going to square both sides. So that gives me c squared is equal to 2gm over the Schwarzschild radius. I'm going to multiply both sides by the Schwarzschild radius because I want it to be on top. These are going to cancel out. I get Schwarzschild radius times c squared, 2gm. I want Schwarzschild radius by itself, so I'm going to divide both sides by c squared. And I get that the Schwarzschild radius is equal to 2gm over c squared. So this is the radius at which light can no longer escape from a black hole. If you go out farther than that, light can get away. If you go closer in, light can't get away. Right? The deeper you are in this dip, the faster you have to go to get out. So, here is my Schwarzschild radius. So, if you're deeper in this dip than the Schwarzschild radius, you have to go faster than the speed of light to get out. And that can't happen. Right? If you're out here, if you go fast enough, you can get out. If you're right here on the Schwarzschild radius, you have to be going the speed of light to get out. And inside it, you have to go faster than the speed of light. Okay? So, this, this is just a radius. If you make a sphere surrounding the center of a black hole, and that sphere is of radius your Schwarzschild radius, that is called the event horizon. So the event horizon is a sphere, and the surface area is 4 pi squared. 4 pi r Schwarzschild squared. Centered on the black hole. Okay, so these two concepts, this Schwarzschild and the event horizon, they're very, very entwined, right? The Schwarzschild radius is just the radius to your event horizon, and the event horizon is the sphere at that radius. Okay? So outside of this event horizon, there's still gravity from this black hole, right? If this event horizon's down here, there's still all of this gravitational influence all the way to out here. But light can escape, and some other things can escape if they're going fast enough. So looking at this formula for a Schwarzschild radius, 2 is a constant, g is a constant, this is this gravitational constant, it's just a number, it doesn't change. C is a constant, this is the speed of light, it doesn't change. The only thing in this formula that can change is the mass. As we see, if mass goes up, your Schwarzschild radius will go up. So that means as a black hole gains mass, as more and more stuff gets sucked into it, its Schwarzschild radius is actually going to increase. And the event horizon is going to get bigger as a black hole gains mass. Right? And if you have a mass and you squeeze it down into this Schwarzschild radius, then it technically becomes a black hole, right? Because if you are on that surface of it, then your escape velocity is greater than the speed of light. So for an actual black hole, at the center of it, the black hole itself is a singularity, right? It's everything compressed into a single point. This Schwarzschild radius is not like a physical radius, this event horizon. If you get there, you're not going to put your hand up against and touch the side of a black hole. There's no physical size to it. It's an effective radius. But if I were to compress something down to smaller than the Schwarzschild radius based on its mass, then it would also become, in essence, a black hole, right? Because it would become so dense that at that Schwarzschild radius, light could not escape anymore. And that is an important thing to note. So how do we know that, where black holes are? How do we know that they exist? So for some of them, like for the one in the center of our galaxy, we see stars around it, and we see the orbit of stars around it. But for black holes that are just like a couple solar masses, then how do we know that they're there? So, a black hole, it can be they form from these, one way that, the way that we know they form is these collapsing stars, these, or exploding stars. The core, this neutron star, right, it collapses down, and it has to be at least 4 solar masses, or 3 or 4 solar masses, to overcome that electron or neutron degeneracy pressure and collapse down. So theoretically, you could have a black hole that's smaller than 3 solar masses. We just don't really know how it would form, because you need that much mass to overcome this degeneracy pressure. So there's nothing stopping them from existing, but we don't know how to make them. And black holes can get bigger by sucking in more matter or by colliding with another black hole. And then you can get up to these supermassive black holes that are in the center of galaxies. So how do we know where, like, normal solar mass size black holes are? So what happens is we're looking up at the sky, and they see a radio source, something, or an X-ray source, something that is giving off these hard X-rays. And they point their telescope at that point, and they see a star that is moving in a circle, right? They see something that looks like, if you remember from the last thing, when we had 2 stars that were going around each other, right, we get these radial velocity curves when we measure them, right? And the curve looks like this for one of them, and then the more massive star, the curve would look like this. And we can measure the mass from these curves. So we look up at this spot that's giving off these X-rays, and we see one star going around nothing. And so we can measure from its curve how big or how massive this thing that we don't see is. And we say, okay, well, it's not a white dwarf because it's too big, because a white dwarf can only be, 1.4 solar masses. That's the Chandrasekhar limit for white dwarfs. It has to be bigger than that from its curve. So we know it's not a white dwarf. If it were a normal star, we would see it. It would be bright enough for us to see. But we don't see anything there. There's just something emitting these X-rays. And we know something that emits X-rays that you can't actually see is a black hole, right? You've got a black hole, and you've got that gas accretion that can put off these X-rays. But when we look at it with like visible light, we don't see anything. So it's something that's giving off X-rays as part of a binary system. Right? Binary system is these 2 going around each other. But we can't see the second star. So we know it's not a star, it's a black hole. So looking at the homework problems, problem 3 says, what is the evidence for black holes of the 3 to 10 M sun or solar mass variety? That's just what we were talking about here. A binary system that emits X-rays where there's an unseen companion that has mass at least 3 solar masses, but a main sequence star or giant would be visible. So one example of this is this system Cygnus X1. We see the star going in a circle. We can measure the mass of whatever's right here, but we don't see anything there. But it's giving off X-rays, so we know it's a black hole. So if the Earth could be compressed to a small enough radius, it would become a black hole. What is that critical radius? So the radius at which something, if you squeeze it down into, becomes a black hole is the radius at which light can't escape anymore. And that's that Schwarzschild radius. So that formula that we derived for Schwarzschild radius is 2gm over c squared. So for the Earth, this symbol, this circle with the crosses is for the Earth, is 2. G is 6.67 times 10 to the negative 8. And this is centimeters cubed per gram second squared. Right. Yeah. And then the mass of the Earth is 6 times 10 to the 27 grams over c squared. Do 3 times 10 to the 10 centimeters, 3 times 10 to the 10 centimeters, right? I'm doing c squared, so c times c. So then, since these are all in scientific notation, I want to multiply and divide my exponent, or my coefficients. I'm going to do 2 times 6.67 times 6 divided by 3 times 3. And then I add or subtract my exponents. So I'm going to add 8 and 27 minus 10 minus 10. So that is negative 1. So that is, if I do that math, it's going to give me 8.9 times 10 to the negative 1. I want to look at what my units are going to be. So I know I want a unit of length, right? Because I'm looking for a distance. And I want to check and make sure my units are right. So I have 3 centimeters on top. Down here in the bottom, I have 2 centimeters. So I can cross off 2 of those and 2 of these, leaving me with 1 centimeter up here. So this is per second. A grams on bottom here and a gram on top here. I can cross those out. Down up here, I have 2 seconds on bottom, and down here, I have 2 seconds on bottom. So I can cross off those 2 and those 2, and I'm left with just 1 centimeter, which is what I want. Right, so I'm just plugging everything into this formula and calculating my answer. So, which of the following are true and which are false in describing an event horizon? It is the distance from a singularity where the escape velocity is the speed of light. That is true. That is the definition of an event horizon. What's the surface at that distance? It is the extent of the gravitational influence of a black hole. That's false, right? There's all that. If the event horizon is here, there's all this gravitational influence still for this black hole. It's just light can escape it. Light's still being pulled towards it. It's just able to go fast enough to escape it. And then only black holes that are 3 sun or larger have an event horizon. So that's false, right? There's no minimum amount in this equation, right? You can put any mass in here. So any mass black hole would have an event horizon. We just don't know how a smaller one would form in the first place. And then the size of the event horizon of a black hole increases as mass is added to the black hole. And that's true, right? As mass goes up, the Schwarzschild radius goes up, and the event horizon increases. So there's 2 more homework problems for this section. 8 says compare the escape velocity from the surface of the Earth for a hydrogen atom with a mass of 3 times 10 to the negative 24 grams, and for the space shuttle with a mass of 10 to the 7 grams. So when I look at this formula for escape velocity, square root of 2gm over r. Remember, this mass is what we're trying to get away from. And there's nowhere in this equation for me to put the mass of what is trying to get away, right? So that tells me that it doesn't matter how big something trying to get away is. It has to go at the same speed no matter how big it is to get away from this mass. So this hydrogen atom and this space shuttle are going to have the same escape velocity no matter what, as long as they're escaping from the same mass and the same location. So this escape velocity is independent of mass of the thing trying to escape. And then question 9 says, to the best of our knowledge, neutron degeneracy can only support a mass up to 3 solar masses. If mass is added to a neutron star and this limit is exceeded, what prevents the star from collapsing? And the answer is nothing. It's going to collapse. It's going to collapse down into a singularity and form a black hole. Okay? So that is the end of this part on relativity and black holes. I'm going to do one more video on the supernova type 1 and novae and how we get heavier elements. I'm going to try to do some math examples that I can put up if I have some time. If you guys have any questions, please email me. I hope this has been helpful.